Okay, well, I don't know why this class seems to only have 4 people in it now. That's not what my roster says.
Is
Uh,
there a lot of people here on Monday or no?
I mean, maybe 5?
yeah. Well, there'll be more on Friday because we have a quiz.
And let me guess, you've not received a single email.
Oh, no. So quiz 1 is Friday. And then exam 1, yep, is a week from Friday. And the topics for that, let's go up through linear interpolation. And so we're going to finish talking about linear interpolation today.
And so those 4 practice problem sheets, those are like going to be the best thing.
Yeah, exactly.
Got it.
And I'm also going to give you a weekly assignment soon, and those will also be, similar types of problems and, good preparation for the exam. Although I guess you don't have solutions to any of those.
And we'll probably have the quizzes by then and
Yeah.
just have everything.
Yeah. But the quizzes and the exams are totally separate things. Like there's no crossover in the kinds of questions I would ask, really. The exams are like the homework. The way to get ready is the homework.
And the quizzes are
just reading your notes.
Conceptual.
Yeah. Right. It's really just remembering. It's not even conceptual. It's just like making sure you're reading your notes.
And there's none of that on the exam.
Right.
The exam
None of that.
Only like math.
Right. I mean, indirectly, but yeah, there's no questions like quiz questions on the exams.
Got it.
But it's still going to be important that I remember like the differential.
Yeah, right. Like, yeah, exactly. Indirectly, they are sort of connected. If they weren't indirectly connected, I wouldn't care if you read the notes or not. Actually, if they weren't indirectly connected, I wouldn't be talking in class at all. Okay. So now we're going to do linear interpolation. Of functions with 2 independent variables. And so what we're talking about now is, so what we had before was like this. Here's our independent variable. And there's our function. And we have an x1, an x2, and then an x. And we're using these known values here, assuming that the function between them is linear, even though we know that's not true, and then approximating like that. In the case of 2 independent variables, so now our function looks like that. Our space of independent variables looks like this. And what we have is something like we have x1, x2, and then the x that we want. And over here we have y1, y2, and the y that we want. And let's see. Okay, so now we know these 4 points. And we're assuming that there is a plane here, and we're going to use that even though it's not a plane, you know, and we're using that to approximate our the value we want. I don't like how that plane looks though.
And the value is coming out as a point on the surface?
Yes.
Okay.
So with 2 independent variables, you need to give a value of x and a value of y, say, to find a value of the function, to find the height of this surface. And we're going to use, this got a little ugly. I'm going to try again though. Okay.
So you could kind of say like you're assuming it's planar between your known z's.
You're assuming that, so you know the 4 points, the 4 corners, okay? You know the value of the function at x1 and x2, y1 and y1 and y2. So there are four, so in the space just of the independent variables, we have 4 corners, you know. Let me draw it from below. So if you're just looking down from above, ignoring that that surface is there, you have an x1, an x2, a y1, and a y2. And you're trying to approximate the value at x, y. Okay, and you know the value of the function at these 4 points, x1, y1, x2, y1, x1, y2, and x2, y2. Okay, and now you're assuming that the function is a plane in between those 4 things, and you're using that plane to figure out what the value, what the height is of this surface at x, y. Okay, it's the same idea as this, but it's harder to visualize, you know.
And so we just assume that that center plane is a flat plane.
Yes, that's right.
Okay.
Yes, the same way we assumed that the function connecting x1 and y1, we assumed it was a line. You know, it's the same idea.
That's the approximation.
Yeah.
And if you wanted to get like a more exact number, you would just take the limit as
Yeah, you would take those points closer together.
they approach x.
Yep, that's right. The closer you get, the better it is, generally.
Okay.
Okay, so how do we do this? So to approximate f of xy, we start with known values, and let me say 4 known values. And I'm gonna put them in a format like this picture here, like we're looking down on the space of independent variables from above. So we're gonna start with knowing the value of f of x1, y1, f of x2, y1, f of x1, y2, and f of x2, y2. And we're going to do 3 applications of the linear interpolation equation we had from last time. So the first one, we're going to approximate. So notice that, just keep in mind what we know and what we want. So we know the values at all of these combinations of x1, x2, y1, and y2, and we want to know at x and y, okay, at x, y. So first we're going to go, we're going to say f at x, y1, is approximated by f at x1, y1, plus f at x2, y1, minus f of x1, y1, over x2 minus x1, times x minus x1. Okay, so the first thing we're doing is, okay, we're going to assume that y1 is a constant, and we're just going to do a linear approximation using x1 and x2 to find the value at x. So let me show you. So if this is, okay, so this is x1, x2, y1, y2. Now we're approximating the value here at, this is at x, y1. And then we want to approximate the value straight above this at x, y2. So the second thing we're going to do is we're going to approximate f of x, y2 as f of x1, y2 plus f of x2, y2 minus f of x1, y2 divided by x2 minus x1 times x minus x1. And so what we're doing here now is this is our x1, this is our x2, y1, y2, and we're approximating the value at x y2.
And then you just recombine.
And now we're gonna do it now that we have these two values on a line, you know, now we're gonna do a linear approximation along this line to get our final value. So the third one is f of xy is approximated by f of x y1 plus f of x y2 minus f of x y1 divided by y2 minus y1 times y minus y1. So now that we've done it for the top and bottom values at x, now we can assume x is constant and finally do our interpolation on y. And yeah,
Oh, wait.
let me just draw this. Okay, so here's our x1, x2, y1, y2. Now we have this line. And now we're going to approximate there, and this is x, y. Now we're going to be getting these values like from a table. And in a table, there's no like, I mean, we're used to x coming first, y coming second. There's no first and second when you're talking about properties. You just need two properties to define a third property, as long as you're not at a saturation point. Remember talking about that? When you're at saturation, you only need one property to figure out all the other properties. When you're not at saturation, you need two. So you can call whichever one you want, the first one and the second one. That doesn't matter. Okay, so let's see how this works. Did you have a question?
I just wanted to, I didn't quite write down the second one.
Yeah. Second one.
Yeah.
Yeah.
X.
I have to be honest, I think, to me, it's easier to think how this, it's easier to put the notes aside and imagine how this must probably work than it is to try to follow all the notation. You know what I mean? Like,
you're taking the smaller value and then you're finding the rate of change between the two and you're multiplying it by the actual change that's happening.
yes, that's right. And we're just doing it sort of in two steps. I mean, it's actually three steps, but we're doing it first to get interpolating over x, and then using that to interpolate over y in the two-dimensional case. Okay, so let's see how this works with a mathematical function. And then we'll do it with a table.
And in like exam problems with multiple factors, like you would want us to complete it and take that approximation of the line.
That's right. And maybe I'll do mathematical functions, but I'll more likely just give you values from a table and say like, what's the best approximation? And another thing I want to say is, okay, so there's no obvious first or second property when you're talking about material properties. You get slightly different answers depending on which one you choose first and which one you choose second. So it is true they're not exactly the same, but this is an approximation. They're both reasonable approximations. There's no way to choose which one's better, so.
And then my other question was like the point at which you start with will dictate the structure of the rest of the formulas.
Yeah, I guess that's true. Yep, that's right. Okay, so let's, what we're going to do is approximate the function f of xy equals x squared y squared at x equals 2, y equals 2. And we're going to do that by being given so I'm going to give it in this grid pattern. I think it sort of gives you kind of a visual idea, but we're going to be given that f at 1.8, 1.8 is 10.5. F at 1.8, 2.2 is 15.68. F at 2.2, 1.8 is 15.68. I chose this symmetric function, so that's why those two are the same. And then F of 2.2, 2.2 is 23.43. And you can see that, so we're trying to use these values to approximate something that, like when we have the table, we don't know what the true value is, so we don't have anything to compare it to. With a mathematical function, we can just plug these in and see what we're comparing to see how close we are. And you can see that if you plug in 2 and 2, we're trying to approximate a value that we know really should be 16. Okay. So we're using these 4 values that, I mean, 2 of them are close to 16, 2 of them are pretty far from 16, and we're just going to see how close to 16 we get, you know.
Should we be thinking of those values as a depth in the z direction?
Yes, that's right. Think of it as a height, I guess, in the z direction. Yep. So first of all, if we're choosing x as our first variable, we're going to approximate f for x equals 2 at 1.8. And we're going to do that by taking f at 1.8, 1.8, and then adding it to f of 2.2, 1.8 minus f of 1.8, 1.8 divided by 2.2 minus 1.8, and then multiplying this by 2 minus 1.8. And so now all I have to do is just plug in those values. So it's equal to 10.50 plus 15.68 minus 10.50 divided by 0.4 times 0.2, and you get a value of 13.09. Any questions about that first step? Okay, so let's just keep writing all this stuff out. So now I'm going to approximate what are the input arguments that I'm approximating in this second step. Perfect. Yep. 2 and 2.2. And so the first thing is f of what? Yep, 1.8, 2.2. Perfect. And now for the fraction, we're doing rise over run here for the slope. This is f of, what's this first argument?
2.2, 2.2.
Yep, perfect. 2.2, 2.2 minus, and what's this one? 1.8, 2.2. And then 2.2 minus 1.8. And then 2 minus 1.8.
So would this formula be given on the exam, or we just?
Yeah, I'll give you the formula, but not the steps. You know what I mean? Yeah. So then we have 15.68 plus 23.43 minus 15.68 divided by 0.4 times 0.2, and you get 19.56. And now for the last one, what are we trying to approximate? Oh, well, it's the last one, so it's 2.2. And now, 1.2, 1.8. Yeah, right. And so now we're going to do f of 2, 1.8, plus f of 2, 2.2, minus f of 2, 1.8, divided by 2.2 minus 1.8 times 2 minus 1.8. And now we're using the two values that we just calculated. We're not using values that were given initially anymore. So 2, 1.8 is this one, 13.09. 2, 2.2 is 19.56. Then minus 13.09 divided by 0.4 times 0.2, and we get 16.32. Yeah. It's, I don't know, like I said before, I think in a way the notation is so cumbersome that like it makes a lot more sense if you think through it than if you try to understand the notation, you know?
I think it'd be helpful to look at an example where they're not like on the same points.
Yeah, you're probably right about that.
I'm trying to like pull out like what's happening.
Yeah. Okay, so let's do one from a table now. And so these are, okay. Well, so I'm first going to do a saturated example, I guess. We'll just do a bunch of different examples. So let's say, okay, so from a saturation table, and I don't even have written down what, whether this is a saturated vapor or a saturated liquid, but you do know from the fact.
Does it matter?
It doesn't matter with how you do the problem. It only matters that you know which one you're looking up when you look stuff up in the table. In this case, I'm just giving you the values, you know. So from the saturation table for 134A, that's a refrigerant. at -9 degrees Celsius. We're given that the specific internal energy at -8 is 39.38 kilojoules per kilogram. And the specific internal energy at -12 is 34.25 kilojoules per kilogram. And, you know, what we want is at -9. Okay. So since this is saturation, we only have to do this one step of linear interpolation, which is what we much prefer. Specific internal energy at -9 is equal to, let me first just write out kind of the formula here. So it's equal to U at -12 plus U at -8 minus U at -12. Divided by -12, nope, -8 minus -12, times -9 minus -12. By the way, this would work out the same if you did it as, so if I did this as
U of -8
Yep.
plus.
-12, -8, then you'd have -12 minus -8. But if you did all the orders right, you'd get the same answer because it's the same line between the two. And now we're just plugging in the values. So we have 34.25 plus 39.38 minus 34.25 divided by 4 times 3, and you get 38.10 kilojoules per kilogram. Okay, so we're going to do an example with actually, I don't have a 2D example here. What I have instead, okay, so we're going to do one more thing before that, and I guess maybe on Friday we'll do a 2D example, and I'll give you some problems to try to work through, and if you have trouble with them, we can answer them on Friday or whatever. But now I want to talk about quality, the term quality. Of a saturated mix. So remember, a saturated mix is part saturated vapor and part saturated liquid.
And they're just, you have particles moving between phases?
Yeah, you can. If we're doing calculations, they're in equilibrium, so an equal number is going both ways all the time.
Right.
And the quality we call it X, and it's equal to the mass that's in the vapor state divided by the total mass. Or you can also think of that as the sum of the mass of vapor plus the mass of the liquid. So X equals 1 means all saturated vapor. And X equals 0 means all saturated liquid. And this is useful because for any property, and my general property I'm going to call lowercase q, okay, but that could be specific internal energy, specific volume, specific enthalpy, specific entropy. But for any property, the total value of that property is equal to the quality times that property for the saturated vapor plus 1 minus the quality times that property for the saturated liquid. Okay, so if we know what the quality is of a mix that's at saturation, then we can use the table values for saturated liquid and saturated vapor to come up with the value for our specific mix.
And specific materials at equilibrium
yes.
have different qualities.
Well, yeah, I mean, the same material at the same temperature and pressure can have any quality. You need to be able to figure that out somehow. And we'll talk about different ways that you can figure that out in different cases.
But we just have like ideal values based on like FTP for a given substance.
Well, still the quality you wouldn't have any idea. Like basically think of it as, so say that you have a black box and you know it's at atmospheric pressure and 100 degrees Celsius, and you know the material inside is water. That's just not enough information to know what the quality is. It could all be saturated vapor, or it could all be saturated liquid. It could just be sitting there as a liquid ready to boil, or it could be hanging in the air as vapor and ready to condense. But there's no way to know without other information. Okay, so here's our example. So we still have refrigerant 134A. At a saturation state at 9 degrees Celsius. And we're given that the vapor value of the specific internal energy is I wrote this down funny. Okay, so what we're given is, well, we know that it was the liquid before, so we know that the liquid value at a temperature of -9 degrees Celsius was what we calculated, 38.10. you might want to go up here actually, and now that we know that, this is a saturated liquid from our last example. Okay, so we know that from before. And now we also from the table know that for the vapor at -8 degrees Celsius, this is 222.60 kilojoules per kilogram. And at -12 degrees Celsius, this is 220.36 kilojoules per kilogram. One thing you see from this is how much the internal energy has to go up if you're keeping the temperature and pressure the same to go from a liquid, saturated liquid, to a saturated vapor, you know, from 38 to 220 or whatever. And we are given that the quality is 0.3. So of the mass that we have, 30% of it is vapor, 70% of it is liquid. And we want to know what's the specific internal energy of the mix at -9 degrees Celsius. Okay, well, we've already done the interpolation to figure out the liquid internal energy, specific internal energy at -9 degrees Celsius. We just have to do it for the vapor. So for the vapor, the specific internal energy at -9 is equal to the specific internal energy at -12 plus U at -8 minus U at -12 divided by -8 minus -12 times -9 minus -12. That's an approximation. And so that is 220.36 plus 222.60 minus 220.36 divided by 4 times 3. And we get a value of 222.04 kilojoules per kilogram. Now we have the specific, I'm going to write this as UV. So now we have the specific internal energy at -9 degrees Celsius for the vapor and the liquid. And now we can use the quality to come up with our actual total specific internal energy. So for UV, for U at -9, that's going to be 0.3 times UV at -9 plus 0.7 UL at -9. So that's 0.3 times the one we just calculated, 222.04, plus 0.7 times the one we calculated in the last example, 38.10. And we get a total specific internal energy of 93.28 kilojoules per kilogram. And so this is the specific internal energy. So if we now know that we have 5 kilograms of this, we can multiply this by 5, get the total internal energy in our system. And that's a value that we could use in the first law then to calculate heat transfer or whatever.
How would you measure quality?
There's a few ways to measure it. One, you could measure the volume that it takes up. So if you know what the pressure is, and you measure the volume, the table will tell you the specific volume of the liquid and the specific volume of the vapor. And so then you can use this equation here with those specific volumes and calculate the quality.
So is there like a kind of gauge that you could have, like on, say, like on a pipe with, say, steam or something going through it? Where you could have smaller.
Yeah.
I'm just trying to imagine, like, if you really had this system, say it was like this big giant boiler or something.
Yeah.
How would you allow the volume to vary?
Well, yeah, I mean, if it's a boiler, then the gas part is going to expand to take up whatever volume it has, Sure. So the volume in a boiler.
Okay.
Then what you'd have to measure is the pressure.
Okay.
Yeah. But yeah, there are measurements you can usually take to get at the stuff you need to calculate that quality.
So, am I thinking about this correctly? We have our dome, right?
Mhm.
One side is 0, one side is 1, and our x is a point along that.
Yes, that's right. So the dome.
Like you were talking about on Friday.
Okay, so the dome. Yeah, so the vapor dome.
Yeah.
Okay, yes. So you can think of if you have this is like a phase transition. And yes, exactly. What you said is exactly right. As you go, each point along this line inside the vapor dome is a different value of the quality.
Linear.
Yeah.
Yeah. Right. Any other questions right now? Okay, that's all.